10.8, Geometric Probability. Now, along the way in your math career, you have learned about probability, and you should have learned that probability is what you want to happen out of all the total possible results that could happen. Now, what you want to happen isn't necessarily always a positive thing. It's simply the event that you are looking for. So keep that in mind. Probability is what you want out of the total possible results. So for geometric probability, our objective in this lesson is to use segment and area models to find the probabilities of events. So probability is the number of favorable outcomes, that's want, out of the number of possible outcomes. This is out of total. And probability can be expressed as a fraction, a decimal, or a percent. So you can say you have a 1 out of 4 chance of pulling the blue marble, or you can have a 0.25 chance of pulling the blue marble out of the bag, or you can have a 25% chance of choosing the blue marble. Now, in geometric probability, we're going to look at either points on a segment or in a region that represent your outcomes. So let's look at our key concept here. Our event is going to be a ratio that involves things like length or area. So let's start with probability and length. It says that point S is somewhere on segment AD. So we have segment ED or AD. And point S is chosen at random. We simply throw a dart at this segment. The probability that S is on BC, this is what we want, is the ratio of the length of segment BC compared to the length of segment AD. So this here is going to be our total. Now, do you remember how to find lengths of segments? Now, when our notation for probability, you have probability of your event. So we want S to be on BC. BC is what we want. AD is our total. Let's look at this in an example. We say that point K is somewhere on ST. It is chosen at random. So we're going from here all the way to here. What is the probability that K lies on segment QR? So from here to here is what we want. So how do we find lengths of segments? This is our ruler postulate. Ruler postulate says that the length of AB is the absolute value of the difference of A minus B. I knew you'd remember it. So what we want goes from 5 to 8, which would be -3, but that's absolute value. So that's 3. Over our total goes from 2 to 14. Be careful there, it doesn't start at 0, which is a -12, but its absolute value takes care of that. It's a 3 out of 12, or we reduce it, always reduce your fractions, or a 1 out of 4 probability. Probability that your dart will land on segment QR is a 1 in 4 probability. So once again, very quickly here, it's your turn. Go ahead and pause the video and do the next problem. These first problems are always nice and easy. We're told that point H is going to be on ST, segment ST somewhere. We choose it at random. We want to know the probability that our dart H will land on segment SR. So SR is what we want. Once again, our green one, ST, is our total. So the length of SR is 2 minus 8. Absolute value is 6 units. Length of our total ST is 2 minus 14. So absolute value is 12 units. The probability that H will be on segment SR is the length of SR, which is what we want. This is want, over ST, which is total. And it's a 6 out of 12. Reduce that is a 1 out of 2 possibility, which can also be written as 50%. And you can see that our blue line there is half of the green one. So we have a 1 in 2 chance or a 50% chance. Let's take a look at problem 2, using segments to find probability. Now these are some nice real life situations here. We're told a commuter train runs every 25 minutes. I'm going to do that in this color. Every 25 minutes. If a commuter arrives at the station at a random time, didn't bother to check their train schedules, what is the probability that the commuter will have to wait at least 10 minutes? So this is what we want here. At least 10 minutes. Wait at least 10 minutes for a train. So what does that mean? That means that we'll be waiting 10 minutes at the least, so that is greater than or equal to 10 minutes. Well, if we look at, here's our total, right? That's our total. If you get there right when the train pulls up, you're waiting 0 minutes. If you get there right as the train is leaving, you're waiting 25 minutes. Anything in between is something in the middle. Now we want to find 10 minutes. Where will we be waiting 10 minutes? Well, right here is 10 minutes, right? 15 to 25 minutes for the next train. This is 10 minutes till the next train comes. We want to wait greater than 10 minutes. So if we arrive here at 20, would that be more than 10 minutes? No, that would only be 5 minutes. So we are looking for this time frame. This is going to be greater than or equal to 10 minutes. So now we have the probability of waiting at least 10 minutes, greater than or equal to 10 minutes, is the length of the favorable segment. Now this time favorable is not necessarily a positive thing, but it's what we are after. So greater than 10 minutes is 0 to 15 is 15 minutes long. Out of our total possible wait is 0 to 25, so that's 25 minutes long. We have a 3 out of 5 chance of waiting 10 minutes or more, which 3 out of 5 turns into 60%. And guess what? It's already time for you to do one. So when you are doing these problems, draw your line segment to model the situation, and then find the positions on that line segment. So pause the video and do the next problem. Now this problem you had to think a little bit. It said, what is the probability that you will have to wait no more than 5 minutes? Now this is an ideal situation for commuting. You want to get to the train station and wait less than or equal to 5 minutes. No more than 5. That means we're willing to wait 5 or less. So no more than 5 minutes. So our total possibility is we get there as the train is leaving and wait 25 minutes for the next one. That's our green. And when do we get there and only have to wait 5 minutes for the next train? Well, that happens here at 20 minutes into the schedule. And we want less than 5 minutes, so anything 20, 21, 22, 23, 24, right at 25. This blue section is what we're after this time. That's what we want. So the probability of waiting less than or equal to 5 minutes, what we want is from 20 to 25. And our total, this is our want here, and this is our total. And so we get a 1 out of 5 chance or a 20% chance. We have a lot better chance of waiting 10 minutes or more than we do 5 minutes or less, which makes sense. 25 minutes between trains. I think the lesson here is check your train schedule so that you can get there and not have to wait. But you see how probability works on a number line. On to our next concept. We are going to be comparing areas. Now, probability and area is exactly the same thing, only instead of comparing lengths, we're comparing areas. Again, we're throwing our dart. It'll land at point S, is in region R, so in our quadrilateral here. We want to know the probability that S is going to land inside this triangle. So that's inside the area N. That's what we want. The total possibilities are that it lands here in area R. So the probability is just area of what we want compared to the area of everything that's possible. So not a big deal here. Not really a new idea, just using area. Let's look at our first problem. We have a circle inscribed in a square. So those are two things we know how to find the area of. Point Q will land somewhere in the square. Our dart is going to land somewhere in this square. What is the probability that it lands in the shaded region? We do not want the circle, we want the shaded region. Well, how do we get the shaded region? This is a scissors problem. So we have our square and we want to remove, we want to cut out, we want to subtract the area of the circle. So the area of the shaded region, this is what we want, is the area of the square minus the area of the circle. Well, what do we know about an area of a square? It's base times height. Well, what do we know about a square? This is 6 centimeters as well. So we know that base equals 6 centimeters, height equals 6 centimeters. We can find our area of our square is going to be 36 centimeters squared. Now, how are we going to deal with our circle? Well, what do we use for a circle? We use radius. How long is this radius? We know the area of a circle is pi r squared. What's the radius of this circle? Well, if we look here, the diameter is just the length of the bottom of the square there, so we know our radius is half of that, is 3 centimeters. So the area of our circle is going to be pi r squared, 9 pi centimeters squared. So what are we going to do with that? We are going to take the area of our square and subtract the area of our circle. So we get 36 minus 9 pi. And what is our total possibility? Well, the total possibility is the area of the square. So this here, do that in a different color. The total possibility, that's not where I want to write that. This is the total possibility here. It can land anywhere in the square. So up here is what I want over the square. And we know the square is 36 centimeters squared. So what I want is 36 minus 9 pi over total is 36. The probability that it lies in that region is 36 minus 9 pi out of 36, or 0.215, or 21.5%. All right, and once again, it is already your turn to do the next problem. This problem was just like the last one. We have a triangle inscribed inside of a square, and we want our dart to hit the shaded region. So we need to find our area of a square. Base times height is 5 times 5, 25 inches squared. Find the area of our triangle. The height of our triangle is the same as the height of our square. The base of our triangle is the same as the base of our square. So 1/2 base times height, so that becomes 12.5 inches squared. The probability that it'll land in the shaded region is what we want. And how do we get what we want? We take our square, the area of the square, and we subtract out the triangle. So area of the square minus area of the triangle. Out of our total, where can it possibly land? Anywhere in that square. So that's the area of the square. And we end up with a 1 out of 2 chance, or a 50% chance, which should not surprise you at all, because a triangle that touches both of your bases and the top like that is just half of a square. We've seen that happen before. All right, our last problem here. If we're given an archery target, has 5 colored scoring zones formed by concentric circles, that means they all have the same center, and its diameter is 122 centimeters. The radius of the yellow zone in the center is 12.2 centimeters, and each of the other zones, red, blue, black, is also 12.2 centimeters. So we could just imagine a little semicircle here, right? This is 12.2 centimeters. And then we get our next circle here, another 12.2 centimeters. My circles aren't going to be very circly at this point. 12.2 centimeters. And what is that? Yellow, red, blue. We need one more black. Ooh. Not very circly there at the end, but that's all right. So you can see, because what do we know? We know area of a circle is pi r squared. That's why I drew that. I want my radii. So this would be the yellow radius right here. How do we get red? You're subtracting out a circle in the middle to find the area of each one of those. So if we want to hit the red zone, the area of the red circle would be the entire circle, but we only want the donut part of it, and we would subtract out the yellow. So area of the red donut would equal, oh, we'll call that pink. Area pink, the whole filled in circle, the whole donut minus the yellow donut hole, right? So our whole donut here, pi times, what would that be? 24.4 squared, and we would subtract off pi times 12.2 squared. And that would get the area of the red donut. That would be what we want. What would our total area be? That's everybody, right? That's all the way out to black. That's this and this and this and this, right? So that would be pi times, how many of those are there? 1, 2, 3, 4 of those. Now the entire target, 122. So the diameter is 122. So our radius is 61 centimeters. So 61 squared. So this is what we want up top, the red donut, out of the total everything that we can hit. Oh, it's because we have a fifth colored zone out there. It's a white zone, isn't it? That's not black. This white zone out here, that's another 12.2. So there's 5 of those. 1, 2, 3, 4, 5. So that's where we get our 61. All right. The last problem, I'm not going to make you do that one. Maybe we'll take a look at it here. You can look here. We have the area of our red donut divided by the area of the entire target. You can see how that works. So on the last one, what is the probability that a arrow hits the yellow zone? Oh, that's easy. The yellow is just in the middle. Probability of yellow. What do we want? Area of yellow divided by area total. So that would just be area of our yellow circle is pi times 12.2 squared over our area total. We already did that one. Area total is pi times 61 squared. And that would give us a probability of yellow, if we throw that into our calculator, of 0.04 as a decimal. So you have a 4% chance of hitting the center of the target. That's why archery is so difficult. So think of these when you do these problems. These are just simple areas or simple lengths. But on these simple areas, think, are you doing a glue stick problem or a scissors problem? What do you want? What is the total possible things that can happen? On the segment problems, it's just, do I want to wait more than 10 minutes or do I want to wait less than 10 minutes? And you have to decide which direction you're going. Either way, on any of these, diagrams are your friend. So you know, draw, 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 label, 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 and color definitely helps. All right, Well, I think you will enjoy probability. This is a nice way to end this chapter. I think you will have fun doing these problems. And don't forget to do your video quiz.